All right, so thanks a lot. I'm going to discuss gravitational waves, so I also do other stuff. But for this audience, I guess that's enough. And if you want to discuss this kind of topics, I'm very happy to have a discussion this week. I'm going to give a kind of informal talk on filling gaps in gravitational wave searches because they offer new opportunities that are normally not stressed so much, I would say. Partly because of sociology, I think. All right, so well, that's my opinion. So let's see if this triggers also some discussion. So my work is going to be focused, my talk, on two particular bands in the spectrum. The microhertz is described in these papers, and the gigahertz in this paper. And this has been done with a number of great people. So it's not new for you, the fact that when you look at the same object with different bands, right, you see those things which are totally different. We have been, the 20th century has been the century where astronomy has opened the broadband of light to discover that the universe is full of things that we could not even imagine. Now, the question is, what is going on now with they shouldn't be here. Oh, my joke is gone. Anyways, that's the compilation of different possibilities that may happen in the future regarding where we stand in the spectrum of gravitational waves. Again, this is a paper by the author of these lines here. And in this spectrum, well, we see first that we can cover an amazing amount of wavelengths, right? But even with the most optimistic, this is super optimistic. It's as optimistic, and there's no joke, as saying that Terminator is going to happen in 2029, right? So this is why I like to say that this is to be taken with a grain of salt. But still, you see there are some gaps in this spectrum. Here, one between the CMB and the pulsar timing arrays, and there is another one. Because this Muare is super futuristic, so there's another one between LISA and Escalating. And finally, we cover very well these lines. This can be up and down. Finally, there is a mystery of what happens at high frequencies that people don't talk so much about, right? So my point is that there is this possibility of both trying to explore new signals there, but also trying to see how to detect gravitational waves efficiently in these different places. Of course, if your method by chance is overlapping with LISA, well, you have to hurry up because at some point LISA will be much better than you, most likely. I forgot to say that here there is also other very exciting possibilities to use galactic observations of Theia or even Gaia to constrain things on the same order, more or less at the scale. You win a bit more, but still the gap remains.
No, it covers the gap.
Fully.
Yeah, fully, all the way to LISA.
But do they meet like this, or is
right in the middle?
All right.
So below SKA, okay, so better sensitivity, and it covers all the way to it. Okay.
All right. Well,
but paper with the
I have hurry up also. And also another point I want to make is I think that there is
astrometry, by the way.
Sorry? Astrometry, yeah. There is a part of sociology on the kind of signals that we are looking for and we are exploring normally, when, in particular for signals. It's true that LISA and SKA pick up frequencies which are even maybe miraculously corresponding to kind of interesting physics. But also in between, there is also this gap that may be covered in the future, where when you describe a new background, you also it's interesting. I think that you try to move it all around from SKA to LISA because this gap may be covered in the future. So LISA is a carrot in front of the theorist's eyes, and you see it in the papers that typically you want to go there because that will. But also in between, there's going to be something in the future. In this gap. These lines correspond to spectral distortions. So it's funny that the gravitational waves kind of are at these low frequencies, and if they are so intense, they heat up the the CMB a little bit. I don't know if there is anything better there. So you want to think about, and also the kind of signals that you would explore in this direction are a bit hard because they're going to be most likely cosmological, and then you will expect the CMB to also be winning, but you know. And then this other gap, I will discuss later. Right. So first, I'm going to discuss the microhertz a little bit. Again, up to future missions of astrometry that I have not. This is today, I think, the constraints that we have. Right? This is today. I think that today we don't have more than this in this band. So there is at least LIGO Virgo Cagra. There are the pulsar timing arrays, okay, that provide give you this, and there are a couple of observations here. One of them is the Cassini, so observation of a spacecraft orbiting the solar system. And this yellow band is studying the seismographs in the Earth. And you know, if the gravitational waves are strong enough, they are going to excite a normal modes of the Earth, and you can track them. But today, there's no more than this. Right? So the idea is, what do we do there? Yeah, in my talk, we're going to discuss an idea we had with Alex Jenkins. It was a revision of something else that is already discussed in the Missler from Wheeler. The idea that what do you want? That's it. You want something that is somehow between the Earth and galactic scales, either in distance or in time scale. So you're going to look for something that absorbs gravitational waves days, right? Which are like here, or you need that system that is orbiting at days. Or if you are thinking about something that has to do with not resonant absorption, but with modification of length scales, then you would like also something that has scales between Earth, like kilometers to some parsecs, right? So in the middle, there are binary systems that may be the way to go. That's what we try to work out with Alex. But so the idea is very simple. There are gravitational waves. There is a binary system, and as the gravitational wave comes in, the binary system reacts to it, kind of absorbing it, or just doing nothing if it is not in resonance. Or doing nothing now, just moving it a little bit, but then not doing much. This idea was revisited already in 2013, but we thought that we could do it a bit more systematically. In particular, we did it in the way that I think is more transparent for stochastic backgrounds. So that's how we show. So the first equation is quite simple. So you have a binary system, and imagine that there is no general relativity, there is just Newtonian gravity. So it's going to be the relative distance is going to satisfy Newton's law, and on top of it, there is a perturbation. This perturbation, you can put it to many things. It can be general relativity, post-Newtonian effects, it can be the moon, it can be Jupiter, whatever. If it is a gravitational wave that goes through this system, if you sit on the center of mass, then what happens is that these two guys that are in a geodesic now are going to be in a different geodesic. So the geodesic deviation, so the extra part that you have to put in this equation, is a classical result of general relativity 1, no? Or 2, I don't know. You do it when you study free falling. And now that's it. So you're going to have an orbital motion with an extra perturbation, and this perturbation has a characteristic frequency. You have only one single mode. That means that the things that are conserved in Newtonian dynamics, the period, the eccentricity, or the integral of motion, eventually are going to be modified by this perturbation. And there is a very well-defined method of treating perturbations in Newtonian dynamics. As you can imagine, the people doing orbital dynamics have books about this already, I don't know, 100, 200 years ago, right? Because they were obsessed about getting all these precise calculations for the solar system. So this is a method that is called the osculating orbits method. I don't have time to discuss it, but basically it tells you that for any perturbation that you add to the orbit, you decompose the force, the extra force, into 3 components: radial, in the angular direction, and in the orthogonal direction to this plane. And for each of them, the different orbital elements, which are constant if this is 0, are going to be modified a little bit. So you have to imagine this is only valid for perturbation theory. So you imagine that you always have an orbital motion which is practically elliptical, but with time you can approximate this as an ellipsis that is moving or is kind of doing some kind of motion in the space of orbital parameters. And there is a one-to-one correspondence between these 6 equations and the 6 equations that you have to solve for this orbital motion. Again, this is book stuff. Okay, that it requires some effort to do. It's quite nice. And by the way, you can also derive this way the advance of the perihelium. Well, I didn't tell you what these are. So this is in the previous transparency. The different orbital elements are described here. So this is the pericenter. There is the inclination of the orbit with respect to a reference frame. There is the period. Most important ones are the period, the eccentricity, and the pericenter, because the other ones are not so well measured in general. Typically, the period, for when I'm going to discuss, is the one that drives all the data. So in principle, the rest are not so important. So this is what you see. You have a force. Now you have to tell me what the force is, but once you know this, for one particular, if the force is deterministic, basically you are done. But the force is not deterministic if we are talking about stochastic gravitational waves. So each of these curvatures of the wave comes from a different, in principle, primordial wave or wave in the universe. And this is not gonna be a deterministic system, but a stochastic system. So the force itself, right, is changing with time with a particular spectrum. And then something that we did and was not there in the previous work is to transform this kind of Langevin equation, so an equation on the variables that now are going to be like a stochastic variables, into a Fokker-Planck equation that describes, well, this is the Langevin, so there is a deterministic evolution of a variable plus a stochastic part. In our case, the stochastic part is the force from the gravitational wave. And well, there is a formalism to go from this one to a formalism that just tells you how the distribution is being modified, right? And since we are talking about the stochastic backgrounds for which we know the power spectrum, this is the kind of language that is better, right? Or nice. It is more complex. So the Fokker-Planck basically tells me that now my period, my eccentricity, all the orbital parameters are no longer are now stochastic variables, and they are characterized by a distribution, by omega. And from the evolution that I have from gravitational waves hitting it, I have a way to evolve the distribution, and in the limit that is valid for what we are discussing, it has 2 terms. One is the drift, and one is the distribution. The drift, what it does is basically, you have a distribution which is centered around one point, it drifts the mean value. And the diffusion, what it does, it makes the distribution wide. Of course, there is no Gaussian. I mean, this is the first effect that you're going to see. And so the idea now is that when you study the period over many orbits, you're gonna see that eventually, because it's living in a background of stochastic forces, it's gonna behave like a random variable. And eventually, you can, see that the mean value is gonna evolve, or when you measure the distribution, you're gonna see that the noise level is gonna be higher and higher. Depends on these 2 guys. Now, when is this efficient? Well, this is efficient when you are in resonance with the wave, because otherwise the wave kind of comes and goes, and you are moved a little bit. But if you are in resonance, you absorb it efficiently. And indeed, when you do these calculations, what you see is that both the drift and the diffusion pick up. Well, the drift has a deterministic part, and in the part that has to do with the background, it picks up waves that have the frequency precisely, at integral values of the frequency of the wave that arises. Right? And this depends, of course, on the eccentricity. If there is no eccentricity, this is 0. By the way, you need something to distinguish that the wave comes from somewhere. So you need some eccentricity to start with. Otherwise, there is no way.
For
The gravity wave doesn't give drift, just diffusion.
Both.
Also drift.
Yeah, there's both. And the way to understand it somehow is coming from this here. You see, this is not symmetric. So you start with if there is a gravitational wave that comes and makes your orbit have a bit more of a longer period, then the next one is going to have even a bigger effect. So you tend to go in the direction of bigger. So you tend to destroy the gravitational waves. They tend to destroy the system because it's not symmetric because you may think that if a different wave comes with the opposite phase, you may do the opposite. But if you decrease the period, then the effect is also decreased. So you tend to in this random walk to destroy. This is the way we understand this.
Yeah. It's like geometric mean.
Exactly.
More than.
Well,
it's more like shear, no? It's inducing shear on the system.
It's not inducing shear. It's doing
shear.
It's doing both things. Yeah.
So
you see the eccentricities.
Stochastic background destroys the system.
Yeah, you put a binary system with a little eccentricity to start with, otherwise it's close to zero. Then it will heat up the system. It will destroy it. You have to be on resonance, so otherwise it will take forever. So with this in mind, once we derived the math, we had a look at which systems could be used for this. We were always focusing on binary pulsars, right? Because we knew from previous work that they were a good system for this because their orbital motions are tracked to very high precision, and all the systematics are very well understood. So you can just basically the way they do the data analysis is they give you a p as a period, so a p dot. They basically give you a bound on this new parameter that you can, and they give you a time series. You can do a very nice analysis. And then when we were about to finish, we also realized that there is now it's obvious that in principle the moon orbit is also being tracked with high precision with the lasers that are reflected by these retroreflectors, and we also gave it a try. Finally, there are also satellites that are set.
You have a lot of energy due to the friction of the
sea, right? Exactly,
and that's much bigger than any.
That's much bigger, but again, we don't do the analysis yet. What we take is that they gave us an uncertainty on 30 years of measurement on the period, and then I know that then in 30 years the period has not a new systematic. See what I mean? Yeah. It would be very hard to claim discovery, but to put a constraint that there is no new source of noise, this is what we do. Okay. If we discover something anomalous, it's going to be hard to convince anyone. I fully agree. Yeah. All right. And here is what we have found. Now in this, I have the previous lines here, and here. Now I have also added what these are going to do in the future. It's blue, this PTA. There is LISA. There will be maybe atomic interferometers. ET, I forgot to put what Juan mentioned of astrometric measurements in the future. Today, with the current pulsar timing, we believe we can go all this way down, which is quite nice. With the moon, we can go here, and the difference between this orbit and this is that here we put together many different. You see, you are always on resonance with a frequency, then there is a width that has to do with the eccentricity, because when you are eccentric, you can excite more modes. And here we have many pulsars, and that's why the band coverage is bigger. And this is a satellite. Okay, this satellite is a satellite whose orbital motion is basically chosen by hand. So in principle, if you convince Elon Musk, we could populate many of these parameter space. And the nice thing, by the way, here there is this ineffective line today, an effective line in the future. So this is a kind of a threshold that in principle, you have to beat if you want to be competitive. This is a cosmological constraint. So there are ways to beat it, just theoretically, but it's always nice to put it in the plots. So I think that's the conclusion of this first part, that in 2040, with SKA, you also expect many more pulsars. So in principle, with the kind of recurrence of data that they are going to have, we may go all this way down here if we are lucky. If we go back to the moon and we change the mirrors, we can go all this way down to with moon observation, and with satellites, we expect that this comes from a paper. We didn't invent it. If you go to lunar laser ranging papers, there's a review claiming that in the next 10 years they want to go back with the mirrors. Then they will be able to measure more efficiently, and with this, eventually, this is just a matter of sending a lot of lasers back and forward, and with this we get this kind of constraint. Now, I'm not a person who has been working on any backgrounds on this band, okay? But you see, what you normally, my message on this is that when you, for instance, study first order phase transitions, normally people derive peaks that are basically, always within the LISA range. I understand that that's a very well-motivated physical range, but also I would also want to go back to my first message that I think it would be interesting to push them all the way, which is physically reasonable. I understand that also with my discussions with Danny, that it is very hard to make it exactly in a place where neither LISA or PTA will see it, but the moon will see it. But still, or even if it is complementary, mind that you end up around here, that would be nice. Something which is also great is that there is I guess most people know there is a claim, well, I would say there is a noise in PTA observations. People are trying to see if it is gravitational waves or anything else. It's also great that if it corresponds to supermassive black hole, it has to go up until a place that is not completely understood. But future measurement with the moon may complement this observation. And it would be very beautiful, to be able to see how this signal is, is really what people believe it is. I mean, it's not clear what it is yet, but. And with this, I'm gonna finish my part on microhertz. How much time do I have left?
20 something.
Okay, cool. Yes.
So quick question: what are the lines inside the band?
Which line? These ones, for instance?
No, up there in the lunar band.
This?
The lunar region. Yeah, there are these lines.
This?
Yeah.
That's nothing. Let's check. Yes, to put on the footnote. The caption. The checked part is the one covered by just to make it more apparent that we cover these new regions. Checked is the new region. This is compared to where it's not checked. Is the new region that we will be able to cover. We're already covered. We covered with the subtlety that we have not done yet. We haven't done the analysis. So in principle, it's possible that because what we have to do now is we have to take the time series of pulsar timing or lunar laser ranging, and on top of it, add a new systematic effect that we can compute. But do the Monte Carlo, the Fisher matrices, see if there is some degeneracies in there. It may happen, right? It may happen. So this may be deteriorated a little bit. This kind of theoretical constraint. It will deteriorate for sure a little bit. So for instance, the PTA here is not like this, right? There are some frequencies at which you are not so. So I think that's the first message. There may be other ways to go in here. And I think that there is this both theoretical and also, more phenomenological or experimental opportunity to see how to bridge this gap. Yes.
Yeah. So, at which frequency scale is the turnover of the power or signal?
I don't know. I think that's something about the population of the binaries and people of these supermassive black holes. I think that
so
what people know is that
the number density of these guys corresponding to these frequencies.
Exactly.
The signal.
In the same way that you don't know where the population should be, remember that.
You don't know.
Yeah, but the thing is, as he plotted, he made a cutoff there. But of course, in principle, there's going to be a cutoff.
Yeah.
And the question is, at what scale,
Exactly.
more or less, given the uncertainty, we can expect this follow?
This I don't know. If you ask astrophysicists, they always tell you, it's very hard, but I don't know exactly. I would like
Understanding one cannot give a definite answer. There must be some range of.
I agree. I don't know.
So you said that the generic evolution of the system, at least first order perturbations, is that it's destroyed, right?
Yes.
So could you claim that a given system you could not see it?
Yes, that's another way. Exactly, that's another way to look for these gas. For instance, you can look for the less bounded objects in this frequency range. In the galaxy, there are something called white binaries, which are binaries that are super closely bound. Basically, you play a Barca Madrid game, and so they are, and that's a way to look for instance, dark matter also that may be there, and that would be also a different way to look for this, which is also interesting because pulsar timing or the moon, they give you a lot of precision today, but we have very little time of observation, 30 years. In the other case, you have 1 giga-year of time for this to be destroyed. We have not done the calculation. Something we did is to look for instance, you can also heat up the solar system. And for this, you need gravitational waves, which are super a high energy density. But just for fun, in our paper, you want to destroy Pluto, for instance. Yeah. Well, galactic dynamics has also its controversies in the sense that it's a system that is dirty, so you have to take a lot of statistics in the end. So you see one binary system which is there. Also, you can find something we did in our paper. You can find a situation where there's a equilibrium between emitted gravitational waves and absorbed gravitational waves. That means that in the distribution, you may stop at some point where, because you emit gravitational waves, you also you get hotter, what is called, by absorbing you get colder, right? For this you would need systems which are very, emitting gravitational waves intensively, which are not these gas. But population studies is a very interesting way to look for gravitation. I have many ideas on this, but the Oort cloud, for instance, which is also, you cannot do the same you can also think about covering this band with these kind of objects which have periods which are huge. And in the solar system, there is supposed to be a cloud which is bounded, but it's very far away. All right, so that's the idea for the first part. Now let's move to the second one.
Yeah, but I have a very nice question. So at the level of energy density, we're talking about energy density less than CMB. So, binary system doesn't drift because it absorbs CMB photons.
Yeah, but you are never so low in frequency, right? There are no CMB photons, so.
No, this I know that but still the drift is due mainly, if I understand, to the fact that you absorb energy from outside, you know? And this energy is very tiny. So how do I understand this?
Well, the energy balance works. I think that you have to imagine that we are not changing the orbit by a huge amount.
No, I know, but
we have 30 years to change it by a centimeter. Okay. You see, that's what will happen with the moon is to have 30 years to a millimeter. So change the orbit by a millimeter by absorbing on resonance the background. Right? If it is CMB, since you are not in resonance, it's going to be a random walk without.
For me, I need it. That's the difference.
Sorry?
Maybe the difference that there I need the photon. So
maybe
you are not going to enter in resonance with it.
You are never being in resonance
because of the frequency.
No, but a photon on the CMB that goes to the moon stays on the moon.
Well, but this is also what Juan was saying. So we are not more moon experts. We just believe that what they tell us. You see what I mean? They tell me that the orbit of the moon, they also treat the distance, but it's the same as the period, basically. You can trade the period by the peri-astron, whatever. And they tell you that we know this variable with this kind of precision within 30 years. That means that there are dissipation by tide, there are many things that happen, but they know that all this within the error bars, they don't need any other systematic. And what we say is that if we add this on top of it, we expect that you will see it if you are above these lines.
You're mostly sensitive to the drift more than the.
It's a combination, depends on the orbit a bit. All right. But yeah, I agree that it's surprising that these low density energy densities eventually do something to this huge. But think about the precision of which we know the orbit to the moon is also.
But for me, it has to do with the resonance, I mean,
yeah,
of course, I'm pretty sure the system is passed by whatever number of photons from different sources, which are way more intense. But the whole point here is you are entering resonance with these frequencies. And as tiny as the effect is, it grows in time.
It's at least secular.
I think the difference is that the photons we also emit because it's not the full body.
It's also emitted. You mean
so maybe you are in a sort of.
It's also, yeah, the secularity is important. Again, this the fact that it grows over time. We can look into this. Okay, let me go to the next part, the gigahertz. So here, until maybe 3 or 4 years, it was more like cliff than a gap, in the sense that it was not discussed so much, right? This part, and the reason is relatively, it can be understood. I think it has to do with the following thing. So if you think about the standard model sources, forget about this, and you want a coherent source emitting on the megahertz, let's say. So you need something that moves a lot of energy in scales of megahertz. And anything which is astrophysical, either you have it on your background or it's not going to be intense enough to reach it, right? So I think that's why it was not so developed, this part. On the other hand, a stochastic background which arrive all the way to the megahertz, gigahertz, and beyond, they are known. For instance, these are very nice papers in this direction, but as I will show, they are very suppressed. Okay, I will show you. So in principle, it's hard to motivate this just from the at the level of which sources you will have. Again, now that the field is opening, this is no a problem for PSI. So you can also think of this as an opportunity, because precisely since you don't have any coherent source, whatever you find there is going to be a new signal of new physics. So that's the way people have been turning this into an opportunity. There was a meeting like 2 years back, and it was by people interested in these signals, and Danny was part of them. And it was reviewed in this kind of a nice paper. I think it's nice because kind of they made the effort to draw the attention of the community to this possibility. All right. So what can happen here? Well, in principle, the frequency of primordial black holes is not if they are inspiring, it can be very high. Of course, this means also that their lifetime is going to be very low. But eventually, people can come with scenarios where this may happen. There is this phenomenon called super radiance, where basically you are sensitive to the frequency of spinning of a black hole. Okay, this also can populate these high frequencies and other exotic objects that I'm not going to discuss so much. This is DSM or SM, depends on your taste. Okay, you can also put this, but what is there for sure is this kind of thermal. And as I said, this is a recent paper, okay, from this author, Ringbalan, where they have taken a particular model, this SMASH, which is also a model where Guillermo played an important role, right? So this is the background that they have been able to predict with all within all the cosmic history. And you see what I was saying before, that this is not omega anymore, this is the amplitude. And it kind of goes down all the way to, let's say, the ballpark is 10 to the minus 30. And this falls way below what I'm going to discuss today and what people are discussing today, except for something that I don't understand, which is this GB. It's something called Gaussian binning. That's it's a proposal that is there. But I think that for the other kind of ideas that are there in the market, there's a gap. Okay? This gap is a gap of opportunity or a gap of trying to dig it down until some point where you will see a background, or there may be a signal here coming from other guys. Why most of these experiments are higher frequencies than kilohertz is because we are talking about laboratory-based experiments. So the way in which you want to win is because you say, well, I'm going to do laboratory tests. In the laboratory, we can do atomic clocks, which are amazing. We can do, I don't know, all this kind of amazing quantum metrology. So maybe, even if I am discussing things which are so hard to measure, and my laboratory technologies are strong enough to bridge this gap. Well, we are not there yet, but it's very interesting to see people and new ideas on this direction. So I think that the gigahertz centimeter scale is also very. It's a place that nowadays is taking some more inertia. The megahertz too, by the way, the megahertz, which the thing that I'm not going to discuss megahertz because there is also a caveat for gigahertz. There is a bias, is because many of these experiments were designed for actions, where the gigahertz is where people have been exploring more. We have already kind of the technology to explore this better. But in principle, if you can go to megahertz, that's great. Okay. I will show another plot with other possible signals in a couple of slides. So what I'm going to discuss is also not new. It's solved as general relativity, and it's the fact that gravity interacts with light, and in particular, you write down the Einstein-Hilbert action plus electromagnetism, and you expand at first order in the metric. What you find is that apart from the part corresponding to the Maxwell tensors, there is another. There is an interaction which is gravitational wave. So this goes here, okay? Gravitational wave, electromagnetic field, and then it interacts with it generates a current that eventually, when you want to do Feynman diagrams or equations of motion, means that if there is a gravitational wave coming in and there is a background in the middle, it may transform into a photon. Okay, as simple as that. The gravitational waves in the presence of electromagnetic fields may generate photons. And that's, it has a name, which I never know how to pronounce. Guess will.
Gershestein.
Yeah, I say guess will. Gershestein, okay. But it's as simple as that. Now, again, why we are with people got also easily, there is a way to transition between this and things people were doing with action, is that precisely with actions, you have a very similar effect. Actions, there's an electromagnetic field, and you find a new photon. And this is, it was realized long ago, and there's no magic here. So what we have done, and also people before us were doing, but we gave it a new flavor, let's say a more modern flavor, was to explore what happens with electromagnetic cavities in detail. Electromagnetic cavity, you have to imagine that it's a box where the walls are superconducting. In this case, we're talking about superconducting cavities, so modes want to live there for a long time. And if you load them, they stay there for a long time. Okay? So the idea is that I'm gonna put my cavity in the presence of a background field. The background field can be either a static magnetic field or another wave, right? You remember that whatever runs in this line is okay. You see, if it is static, then the frequency of this signal is going to be the same as this one. If it is not static, if it has a frequency, the frequency of this guy is going to be plus minus this two, which you can see from the equations of motion. It is the best I can do with my drawing skills. So the idea is that if this is an empty cavity, so there is no electromagnetic field, if you bring your gravitational waves at the frequency which wants to live, so which exactly corresponds to the one that resonates in this cavity, then I mean you can load it and load it and load it, wait for some time, and then measure if there is something in here. And if there was already a mode, then the good thing about being loaded by a mode is that the final frequency may be the difference between these two. So this allows you to look for, by modifying this frequency to kind of scan a bit more frequency. But in principle, the two ideas are possible. What I'm gonna show you today is only related to this one, okay? Because that's what has been done with action. With action, there is an action that has some frequency. Then now most of the times, then there is a magnetic field, and they try to look also for these electromagnetic waves. But gravity do more than this. Gravity, independently of the previous coupling, can also shake the walls. Okay, can also mean that, imagine that you have this mode here is a normal mode, but now suddenly the walls are smaller. So this is no longer a normal mode. So there will be mode mixing when gravitational waves arrives, and even an empty cavity. That's funny, no? An empty cavity, if you start shaking it, what's going to happen? That by Casimir effect, by dynamical Casimir effect, it may be loaded. So in principle, you can imagine that gravitational waves may generate dynamical Casimir. But this has not been, as far as I understand, developed, maybe because it's still. But if it is loaded with another wave, and then you induce mode mixing, then yes, there is even a proposal that we are revisiting now that explore this idea. But in this talk, I'm just going to discuss this corner. Many other ways of leading to high frequencies. Well, gravitational waves may couple to couple to everything in your lab. They couple to phonons, they couple to magnons, they couple to spins, they couple to everything, right? So I think there is as I don't know what is your taste, but for us as theories of this field, it's very exciting to be able now to talk to these guys doing quantum technologies and try to find a middle ground, because they have the possibility to do amazing stuff, and also I think they are very receptive to us because gravitational waves is so well advertised that they are super excited. Now, of course, it takes some time to build the language, and I think that's what is happening now. That building the language will take some time. Now there will be something that they don't like is this because they are not used to that matter. They don't like this. The idea that they are not going to discover anything is a bit. So the idea that you are constraining is not so well perceived by this community. But
well, a lot of the technology is also present in dark matter.
Right?
And these people are used to just to bounce.
I agree. That's the way to go. There's this dark matter guy that has been there. I agree. But if you talk to a purely quantum guy or girl, they are at some point. This exactly. If you talk about them about the dark matter searches, many people are a bit critical now with this way to look for things that you don't know where they are going to be. Right?
They should be just the opposite.
I
Enthusiastic, because if they're protected,
you'll see. This happens to you. So the way to go here, first, I want to say that there was not always enough attention being paid to the gravitational aspects of this thing. I think, of course, people who know general relativity have done this properly, but there was a confusion, for instance, in some papers using cavities to detect gravitational waves. The choice of frame was wrong. What do I mean by that? That when you study gravitational waves in the TT frame is a frame where the gravity wave is very simple, but the rest of the world is very complex. You see, because you think that the things that in principle for a free-falling guy move, for the TT gauge, they are stationary. So in principle, the first thing to be careful about is that if you want to do all your electromagnetism in the frame which is attached to the laboratory, then you have to take into account that then the wave that arrives is not in TT frame. Again, this is not news for many people, but this induced some error in the past that are not order of magnitude error, but are, if you want to know that it's a gravitational wave coming, you have to be very convincing about how do you interpret the final signal, and if the wave comes this way, the signal is going to be different, and if you put two cavities. Otherwise, if you see a signal in a cavity, it may be an axion, it may be whatever. See, if you want to really establish the signal from a gravitational wave, all these details are very important. Oops, I'm using this one. So the laboratory frame is a frame, basically, that is established by a free-falling person, and then basically the Earth is going to push you up and rotate you. And this is, again, this is standard when you study books on, I don't know, Weber-Blas or where people have been, or gravity in the lab. This is standard. But since the people in the high energy community are used to PT frame for gravitational waves, and then my laboratory experiments, so there was a couple of papers that were wrong in this. Something that is not so well known for, even for gravity people, is the following: that when you explore any gravitational field around a free-falling observer, so basically there is a free-falling observer, and then what the local frame is going to do is accelerate with respect to it. So let's forget about the acceleration that you do afterwards. And by the way, it's never important for us. Why is it never important for us? Because the time scale that this introduces is time scales of order seconds. So if we're talking about gigahertz in resonance, this is never relevant. But anyway, the free-falling person sees incosymmetry plus a perturbation. What is this perturbation? Well, it's given by the curvature measured at your position, and then you multiply by this coordinate. And this is, again, textbook material. But this is true only in the approximation when the time scale and the distance is much more than 1. So this is an approximation where basically, what I said, the curvature. The curvature has two time scales, or this is a wave current. So this is the curvature of a wave, right? So in principle, everything boils down to the frequency of the wave. So when this is small, omega, and then the distance that you are exploring, that's fine. Or in other words, the distance divided by the wavelength of the wave should be small. What are we discussing now? We're discussing cavities where the wavelength of the cavity, the length of the cavity is of the order of the wavelength of the wave. Otherwise, you're not going to stay there, right? So this is not enough. You have to go to next order in this. And this is not even enough. You have to go to all orders in this. And this is not in the books. And we were a bit, oh, no, that's it. Okay, we discovered, I don't have it in this slide, but there is a way to write this to all orders in perturbation theory. So there is a sum, which is basically curvature, position, derivative of the curvature, and then 3 of this, derivative of the derivative. So it's always linear in the curvature because we are always in the regime where h is small. The curvature is order h, so you can be there. And there is a way to put all the terms of first order in h. So this is material from 94, which in this time was purely mathematical. But for these cavities, you need it. Otherwise, you cannot predict properly. And what we did, that was a total surprise, we resum it. So you don't need to go order by order. You can resum it all the way when you have a wave. So when you have a wave, what happens? That the curvature, the derivative of the curvature, the second derivative of the curvature, those are simple objects. And eventually, they boil down to an expression that you can resum.
When you say a wave now, you mean a plane wave with a definite frequency. Right.
A plane wave. But then what you do is you put this, and then the wave packet is something that you can explain. Yeah. Because it's linear. If you have, all this is because it's linear image. If you start to do, this cannot be done, otherwise you'll be solving GR fully.
So is that complex?
Is eventually you have to take the complex. Yeah, this is because we took a partial wave. A wave packet. An exponential. Then you have to take the real part. It's not, as I said, it's not you are making order 1 mistakes. If you don't do this properly, you are making an order 1 mistake. But this order 1 mistake means that you cannot then know properly the prediction. You see, if you expand, order 1 So this is what I had before, and these are other one things. So eventually, but again, to be precise in the lab, this is what you need. You don't need it for LIGO, by the way, because of all the things. You only need it for resonators.
So, Diego,
And you don't need it. Sorry, you don't need it for Weber bars either, because there you need it for resonators, which are light resonators.
in an isotropic space, a gravitational wave is by construction, by definition, the transverse traceless degrees of freedom of metric perturbation. It has nothing to do with choosing a frame. So, because you are not in an isotropic frame, it must be that those terms that are non-vanishing here must depend on whatever distinguishes that from the isotropic frame. So, velocity and acceleration on Earth. But where do I see velocity and acceleration? Here. Just on the curvature, or?
Well, you mean this part?
I'm not sure, because before, when I saw that equation, I was also curious why you don't have it in the Christoffel symbol, like absorbing the space-time field.
I don't really follow. Maybe we're gonna look at it later, because what I can show you is I can show you the full sum, and then maybe the sum can be.
No, but what you show, it just depends on the frequency of the plane wave, the new thing you resume. So
yeah, because it's all for one direction.
yeah. So
Then then the idea is that you have to sum over all directions. And in the final result, you have to consider that you have to sum over all directions. Where are the directions coming from? This is a wave coming in the same direction.
no, but that's not what I'm asking. We're gonna discuss it
But
later.
the question is, where is the gravitational potential of the Earth, for example?
No, I was
There is no
thinking about the fact that it is the fact that Earth is moving, and there is a velocity and acceleration, no? That is changing the fact that you are not in an isotropic space-time pattern.
This is not what we are doing. This is something we will add on top of it.
Okay.
On top of this, you have to then boost your signal.
Okay.
I agree. Yeah.
Okay.
But the reason why this is not so relevant for us is because this boost has time scales which are not going to pick up any resonance. You know what I mean? You add on top of something that oscillates very fast, these things that have some time scale but are much longer. For this kind of resonance, they're going to be important, but they're going to be in principle perturbation. Yes.
Yeah, I just wanted to understand better this point. So the fact that you cannot go to the TT gauge, is it because the Earth is moving, or because there is a gravitational potential of the Earth?
Neither. Because the TT gauge is the second one, yeah. Because you are in the gravitational potential of the Earth. You are a free falling observer.
So that the observer is fixed on Earth, and it's not a free falling observer.
No, you're a free falling observer. It's not a TT gauge observer. That's what I want to say.
Okay.
So the universe, the TT gauge is really attached to the wave. So whenever you do a coordinate choice anywhere in the universe, it's gonna be different. So you have to be careful, and the way to, I think it's also kind of remarkable that it's so simple to construct the local inertial frame. Right?
That's not even to do with the gravitational potential of the Earth.
Not exactly. That comes
An
later.
observer somewhere.
Exactly. You see that all the matter in the universe has generated local inertial frames here, and then on top of this you have to accelerate. But the wave that comes, you know from the wave that the curvature of it, and then that's it. So you don't need to. Something I didn't say, that the curvature is gauge invariant at order age. So you can use the TT gauge form of the curvature to just plug it here. And then everything is determined at first order in perturbation. But at this level, for gravitational waves, it's fine. All right. I guess and with this, you can be very precise about different cavities or cavities that have been used for axions, and which kind of range you expect in amplitude for the gravitational wave. This is still under construction, but some of them which are kind of famous, the ADMX, with some, these are realistic values. And in this range around gigahertz, you can reach 10 to the minus 22. So you are not spectacularly covering this region, but at least there is there is something going on. And well, this is basically what I said. It's very important to be precise. Otherwise, if you see a signal, you don't know what you are seeing. When you do the calculation, and it's in our paper, with a gravitational wave, for instance, what you do is a gravitational wave comes in, let's say, the simplest, you have a cavity which is cylindrical, it comes this way, and it has this kind of polarization going like this, and then that means that the mode that they excite in the cavity is a concrete one. They want to excite modes in the cavity. In the cavity, you can excite anything, let's say, that has boundary conditions that vanish in the boundaries, and the one that the gravitational wave was to excite is a particular one, and by exploring this mode, you can tell that it has been a gravitational wave and not an action. When an action arrives, it likes to basically excite modes. We have more like a feature on the direction of the action, and this is because it's an spin 0, this is an spin 2. So again, if you do this order 1, you're gonna find the same thing. If you do it properly, then you know which modes, and you even, by exploring 2 different modes, you can even know the direction of the wave, for instance. That's very good. All right, this is what I promised to you. This is the pessimistic slide. This is the optimistic, but cheating. Okay. So I had it in. I forgot to add this paper this year by people in Geneva and in Rome. And here is what they want to show is that, again, different observations and possible signals from primordial binaries. Okay. Now they look very, and the strain that they put here is not crazy. It's basically what they expect if they are at the rates of observing 1 per year. So you would say that this is a huge signal, but it's cheating because these guys are in band for very, very little time. So in principle, these observations to achieve this sensitivity, they need to be seeing the signal for some seconds or some minutes, whereas the signal for these guys lasts very little. So in principle, this is kind of trying to be optimistic because the kind of amplitude is big, but when it meets an experiment, it doesn't mean that the experiment should be seeing these guys. All right. So, but that's going in the direction of that new signals may be already.
What is DMR?
This is a radio. Yeah, it's a proposal by here DMR. Yeah, it's what we call a radio. Yeah, it's the proposal by Valerie Domke, Nick Roth, and Camilo. See, okay, what they want, they use another technology that has been used for actions to explore these a bit lower frequencies. Okay, it's very optimistic. It's very optimistic, but again, this has not been built yet. For instance, some of these have been built. This has not. These plans, but I know I forgot how it works. But it's this paper. All right, and with this, I want to finish. Well, look, both. I think this is a very exciting direction. There is, I think, little hope that there is a discovery, but on the other hand, I think it's very interesting to put gravity in all these systems and see which kind of new phenomenology you will find. There is, as I said, a nice dialogue that is being established, and it's being established now. So it is an emerging field. I was hoping that there would be more money from the quantum side because they're supposed to be swimming in money. But they want to get aware funding, so we have to be careful. No, I'm kidding. But yeah, so I say stay tuned because many different groups are thinking about what could bridge this gap, and also at the level of signals. Again, is now that there is more experiments in this plot, I hope that people also get more serious and start to see there are more signals in this gap. And that's all. Thank you.
have been many questions, but since there is only one talk and we still have some time before lunch, anyone?
How does it work, these other proposals of measuring the gravitational rays when coupled to phonons or magnons? Like, are people working actively on that?
Well, for phonons, you can say that that's what people did in the past. You know, the Weber bar.
Yeah.
You excite a mode of the bar. Well, this is there's something called now. There is the next generation of these guys. There are Weber bars, and there are people working. There is not. I don't know. This community is a bit not so much interactive. I don't know really.
There's a group in Australia.
Nautilus.
I was discussing with them in the previous workshop. So the idea is that you have a crystal, and if it's as pure as possible, and with no impurity, so there are no phonons being produced by just simply dislocation and transmission of the stresses all the way to the surface, then when a gravitational wave comes in, it will excite through motions, coherent motions of the whole crystal. It will excite sonar. We work this out with Miguel Montero. And then this transmission would reach the surface. If you had a squid, you have a superconducting detector on the surface, you could even determine the directionality. So it's it's very important for crystals which are not very big, but of course you need many of these. So you would require 1,000 of them.
There is a claim detection, a claim signal, like Toba, but no one has, I think, confirmed it. I don't know which band. I think it's Giga or Megahertz.
100 of megahertz.
And for the spin systems, again, if you think about the spin equation, you think about an spinor. What are they doing? Well, there's really doing that non-relativistic. When you derive the magnetic moment of anything, no? You are doing it starting from special relativity. And then you put this on a curved background, then there's gonna be a modification of order h, and that means again that if there is a magnetic field, a gravitational wave arrives, you may excite the spins. Right? There are some. The best I know is a Japanese group where they use the spin chains to try to detect this. It's not very promising, but maybe there is some other ways to go. Yeah. I was gonna say that the dialogue with the experts on this is not always efficient, because, for instance, these guys are theoretical physicists trying to say what is the best, but maybe you go 2 blocks away and you talk to the experts on magnetism and they say, no, it's better to do this other thing. That's my view.
But you did this for just monochromatic or for?
We did it for monochromatic. Stochastic, we don't know yet. What
so the difference with the action is that the action is monochromatic. So here, if you have a background, you would pay a big price to be on resonance. It will be just very tiny bandwidth that will be affected.
Yeah.
Is this relevant?
No, that's relevant for the signals that, and indeed that's a bit of a mistake. I think this background is stochastic. This is not overplot, okay? But normally when you see this, they are for us, for instance. I don't know if we are here yet. I think we are here, but we have done this for a monochromatic wave. This is a stochastic background, so this is also not clear that we are going to have the same sensitivity.
No, because in action experiment you scan till you look for the resonance. On the other hand, you will never be really on resonance. I mean, you will have something spread out, but it will just pick a narrow energy range.
Yeah, here we have not done the stochastic.
So you can estimate very easily probably the pressure. compared to the peak.
Yeah. We haven't done.
In terms of signals, apart from that one, the left, these frequencies, is there anything proposed?
Well, the most promising one is the one coming from super radiant clouds but then there is no candidate for it. So you need also, it's a bit complicated to think that there is going to be a black hole that has this particular spin that the one that you scan. So I think that the promise in this field is that at some point there will be a battery of experiments, and one of them will pick up the right the right frequency of something, maybe, or that there will be some technology that will do what this GB Gaussian billion that you can see in this paper. They claim. Okay. On the other hand, when you can also say that when they started the LIGO adventure, or even the Weber bars, they had no idea about the signals, or they were claiming they would see something, but it was not true, right?
Well, I think with LIGO adventure there was a clear target, and I think that's what kept it funded. That
but at the beginning,
years,
the beginning was very large,
widely speculated. I think that's a big difference.
Yeah, I think that if you are purist, let's say the only background that is there is something like this, or a bit of a modification of this background, no? Because there is no, as far as I understand also from our conversation, there is no way to make this much more intense. And also from a standard model, there is no way to make here intense stuff. There was a paper last week, I don't know if you saw it, by Barcelona people, where they claim that when two neutron stars collide in the center, you can get regions which are so dense that they may have a phase transition, like in standard QCD, and they will generate a megahertz signal, which is at 10 to the minus 29 or something. I don't know, I didn't get it, but they claim that they may have something to even within the standard model. Again, you require two neutron stars to collide relatively in your back. Well, not so nearby, but again, not something that's going to happen every day. So. No, but it's true. I mean, this is, you want the LIGO adventure now requires bringing this on the way down here. And by the way, they say that this is the ineffective constraint. So, yeah.
I think another aspect that people are going to have to stay taking into account is for very high frequencies, the quantum nature actually of gravity is going to matter a lot, because the occupation number, it really goes to very small numbers. Actually, for backgrounds above 10 to 10 Hertz, our mega gravitational wave background, which could be as large as 10 to minus 9, corresponds to occupation number order 1. Which means you are going to really have to detect graviton by graviton, which probably is going to change any approach about detection or make it even less feasible.
No, which way it goes. It's not coherent.
It's not coherent. It's not a coherent practical background anymore.
Probably the composition will be different.
I think it has to be completely different.
With like photons, when you have gamma rays, it's like CMB.
Photons is borderline. Is precisely this thermal.
Where? Which
equation number is 1. Here it would be
in the CMB. You mean? I agree. That's also nice. There is another topic that again is coming. I mean, it could have been discussed 30 years ago, and it's only because of these new developments that people are thinking about it. No, I agree.
So, about gravity waves from inflation. So, there you can do what you want, no? So that line can be anywhere.
No.
Why not? As long as it goes down, that's fine.
To have a peak.
No, I'm just saying that why you need to commit to a model?
No, because there is already upper bounds in the energy scale of inflation from large.
I know, but this comes from very big scales.
Yes, we is extrapolating to.
This is extrapolating to orders of magnitude. 15.
Sure. What you mean is if you put active source during inflation, you could go above.
If I change the potential during inflation.
No, I think you really need an active source to really break the scaling variance sufficiently, of the background gravitational wave to go above that in a significant manner. It's like for action inflation, you have the gauge field that you excite from the action, they generate gravitational waves, and this gives a blue tilt spectrum, which could go above what the electrode is. But just changing the potential, I don't think we can make. No, actually,
because it goes down because of the slope of the.
Yeah, it goes down because it's plotting the amplitude of the perturbation, which corresponds to a scaling variant background in omega gravitational wave, for instance. But to break that, you need really active stops, to make a blue tilt background very significantly, and there will be a chance, of course.
So I've been talking to different people to see there are ways to even very non-physically increase this in a narrow band. Okay, otherwise you're gonna be breaking this. And ineffective.
Now that I think about it, so as soon as he reaches 10 to 7, 10 to 8, it's gonna fall off necessarily whatever it comes from inflation.
That's I understand, but before
you could go, you could go.
No, not that.
No, you could even go up if you do a very blue tilt background, but of course there is limitations already at how much.
That would be also an interesting plot to see at the same of the black hole, also to see how much. So what is the physical range? Yeah. So what is the
the physical range? I mean, because that's about the horizon scale, for a very large scale inflation, like 10 to 8 hertz. So anything coming from inflation has to come from the left. And said that you could have another shape, but I don't know in these units, these variables, but I really doubt you would reach any of those sensitivities, not even in the best case scenario. I will not show any plot, but I will comment a little bit on the case of action inflation in my talk on Wednesday. You really need very active
Anybody else? No? Okay, then let's thank you again.
Thank you.